So we look at commonly used distributions. So what is a random variable? It's a mapping from sample space to real numbers. But this was in your proper stat course or okay. So you normally think of when we design a system, right? We conduct experiments on the system, right? So you have an experiment will have a set of possible outcomes, right? So that's where we start with. So you have an experiment conducted, leads to a set of outcomes, right? So simple experiment is tossing a coin and the two outcomes are heads or tails, right? So in that case your set of outcomes is just 2, or if you repeat the experiment thrice, right, toss a coin 3 times and then you count the number of heads, right, that is your essentially either outcomes. There are again 8 possible outcomes are there, or maybe multiple possible outcomes are there, right, and so you have this notion of a set of outcomes, right. So for example, some of these I have to write because this is also for NPTEL, right. So if I actually it is not heads or tails, it is head or tail, there is only one coin that you are flipping. So okay, and if you roll a dice with 6 sides, outcome is 1 through 6, right. Then what is a discrete random variable, continuous random variable? The set of outcomes is countably finite, then you have a discrete random variable where your random variable mapping will only have, right, so from subset of, will be several, each of these outcomes you can call an event is going to be mapped to some corresponding probability, right. So if you are measuring in this case, right, so if I toss a coin 10 times and I count the number of heads, that is you are going to have from 0 to 10, right, that is your all possible outcomes for this particular tossing of coin so many number of times. If I look at a system where I measure delay, right, the average delay of a packet, that is no longer countable, right, it can be any value from small value, the smallest possible delay to highest possible delay, depends upon the number of buffers, number of other packets in the system and so on, and therefore that becomes a continuous random variable, right. So you have two classes, discrete and continuous, which by definition one is discrete, one is continuous, so I cannot define any further, right. And when I say finite, I am fudging there because it is countably finite, right. For example, number of packets coming per unit time, number of packets, number of customers arriving to a system per unit time is technically a discrete random variable, but then it could be 0 through infinity, right. So therefore it is not exactly finite, but you know what you are talking about, right. So integer set of values is what the system takes. Okay. So we look at discrete variables first, right, and then later on we look at some of the common continuous distributions. So a random variable say call this x, right. is a function, right, that maps your domain, which is the sample space, the set of possible outcomes, to a real number, which is the probability of each of those outcomes actually happening when the experiment takes place, right. So S is your sample space, right. So X basically associates for every sample or every possible outcome a probability of whether that, what is the probability of that particular outcome happening when the experiment is run, right. So we will just look at one quick example, right. So for example, you toss a coin and let us assume there is a fair coin, right, rise, let X be the number of heads, right. The number of times that heads appears, right, in each experiment. The experiment has actually 3 trials within the same experiment. Okay. So what are the possible values? What is the sample space here? Yeah. Okay. Right, and the corresponding X of S is, okay, will be 0, 1, 1, 2. So it is not a set, it is the corresponding value of S, right. So I'll just leave it this way. Okay, this is where I will have to redo this. Okay, fine. I'll just okay.
So will we not write X of S as 0, 1, 2, 3 and thereafter the probability of S as 1 by 8, 2 by 8 and
yes. So actually if I were to say probability that X equals then you would have your X equals 0 would be, yeah, okay, okay. Okay, we can compute this. This is 1 over 8. So that's your, right, mapping function that maps from your this is your mapping function that maps from that maps each outcome to the corresponding probability, right. And then we have your distribution for the random variable itself. Okay, let's get into a few more definitions, right. sure that okay, so probability mass function, right, is trying to use the, some of these notations are from Trivedi's book, which is a little bit different from here, but for now we will just use this, right, is the probability that the variable x takes the value x. So the mass function defines the probability that random variable takes a given value x, right, and that we will see examples of some of these as we go along. Then you also have the cumulative, right. So f of x is exactly specific. X, I need to use f of t. Okay. So then you have your mean or expectation of so the mean is again x into, I should be again precise, I will have to redo this part, right, value of x and uppercase lowercase is not looking good on the same thing. Okay, with this basic set of definitions we will now look at some of the common variables that many of you probably remember from your other courses. Okay. So this is your first. So the first variable that we will use see often or often see used is the Bernoulli, right, trial of Bernoulli variable. Right. So this is in general any experiment which has two outcomes, right. So an experiment with two outcomes and which we will denote as failure, the value is 0, or success, the value is 1, right, and the probability of success is denoted as p. So this is not your fair coin toss, this is simply some probability of an experiment succeeding or not succeeding. So when you send a packet on the network, the packet either gets delivered or it gets dropped, right, or okay, if you just look at delivery versus dropping, then the probability of successful delivery is p, or dropping is 1 minus p, right. So this would be, yeah. So what is the expectation for this Bernoulli variable? What is the expected value? P? Okay. Then we haven't yet defined the variance, right? P? And what is the variance defined as? What do you define variance? What about the variance? Is also P? Yes. Is that variance definition? Right. So this again we will not spend deriving time deriving that. It's simply P into 1 minus P. And sometimes we also define, right, probability is defined as Q, which is nothing but 1 minus P. So depending on where it is needed, we will use this term Q as we go along. So what is the next possible extension of Bernoulli? If I do repeated trials, right, then what are the other variables that you can derive from Bernoulli? Or one is a geometric variable, right? So the geometric variable is used when you repeat Bernoulli some number of times, repeat it x times, n times, and so on until the first success, right. So that is what you would like to represent with the geometric variable, right. So this represents the number of trials as success, where by trial we mean, I guess, Bernoulli trials, right. Your Bernoulli experiment is what we try to do here. So what is the corresponding mass function, probability mass function for this? So I have x minus 1 failures and finally one success, right. So therefore this is 1 minus P x minus 1, then finally one success, and x can take values from 1 to infinity, right. I need at least one. What is f of x? Your CDF. Okay, this where your summation skills start coming in, right. So what is the summation of this?
Minus P whole power x.
1 minus?
1 minus P whole power.
Sure. You are guessing or guessing? Well, we will skip the minus infinity part, that is irrelevant, so we will at least need less than or equal to x, right. So P so what is no, it does not matter. So what is the expression for that? What's your geometric series summation?
It's 1 minus all the first x will be values. So it is 1 minus p whole square.
Minus, this is the
because
no, I don't. So this is 1 plus, don't we remember the formula for that? Then 1 minus AR divided by 1 minus, I guess 1 minus A depending, right. So you have R terms here or X terms in this case. It will come to finally what you are saying, but that is what 1 by P. That if you are not satisfied, you can go back to your basics and try to solve that. We will use this often when you deal with networks and packet transmissions. Right. Okay, so that is now repeating, right, Bernoulli trials until we get the first success. So that is your geometric series. And where do you find this commonly used in the context of systems networks? What real life example do you have for this geometric variable?
number of retrials.
Yeah, number of retransmissions. When you send a packet and it fails, the probability is 1 minus P if you have to retransmit. So finally the average number of retransmissions needed, right, or the number of retransmissions in the case of repeated, in the case of a link that has got errors and so on, that is what geometric series will try to represent, right, the number of retransmissions needed. So therefore there if you are, oh, is it 1 over P? Yeah. I'm sorry? The number of transmissions, total number of transmissions.
1 over p.
Huh? No, actually 1 over minus P. Yeah.
P will probably have to get this correct. It is a transmission.
Go back to my basics and derive this again. Yes, if P is 1, I only need 1 transmission, right. Not convinced of this, go back and you can derive that. Then your third variable is your binomial. where again I do repeat binomial Bernoulli trials, right. So we will have n such trials. So n trials, and then we count the number of successes. Right. So x is the number of successes when I conducted the experiment k or n times. So the probability that x takes value k, right, or this is what we did with our first example, right. When I have toss the coin thrice, in this case I am conducting n times, and when equals to k, this is your classic binomial, right. And what is the expected value? NP, right. So again you can derive it if you want to, but since you have n trials, and it seems reasonable that P being the probability of success every time, it should be NP. There is also negative binomial, which we do not use a whole lot, so we leave it at that. Okay. Then we come to the classic Poisson process, which is used a whole lot, mainly because it is usually amenable for lots of derivations, right. It is mathematically tractable, and therefore people tend to like this Poisson variable a lot. So we will define the Poisson slightly differently. So if lambda, right, this is the parameter, is the represents the mean number of arrivals. So I have an arrival process. So I am sitting and counting the number of arrivals, the number of packets coming per second, or the number of requests to a cache per unit time, and so on, right. So it is a counting process that keeps track of the number of arrivals in a unit time, and lambda characterizes. So in each of these you will find there is a parameter that characterizes, right. In this case n is the number of trials, p is the probability of success. So likewise here, this is the mean number of arrivals that is either empirically measured or as just assumed, right, to exist. And then you look at some time t, right, some time frame t, where t is the time frame of interest, right. So this is so t is usually considered to be very small, but we will just assume that t is some time frame that you are interested in, and the Poisson process represents the so what we want to do is find out the probability of x number of packets arriving in this time t, right. So x is the number of arrivals in time t. Well, they won't use. where k goes from infinity. Okay. So, the t power minus lambda t to the power k divided by k factorial, that is the probability of having k arrivals in this mean time t. If t is set to 1, then this is of course simply e power minus lambda into lambda to the power k. Okay. So, now let us, this is probably the more important one, right, where we need little couple of more examples. So, let us say that, say lambda is 10, right, and t is 1. So, many times we want to find out the probability of x number of packets coming per unit time, right. So, what is the probability that no packet will come to the system in one time unit. So, even though lambda is 10, right, there is still a non-zero probability that there will be no packet coming in this unit window of time 1. So, what is that value? E power minus 10, right. What is e power minus 10? Very small value. Next time we have calculators, there is 604 students know they need the calculator. 45.39. So, small but negligibly small, right. So, that is your, and if you look at the probability of 10 packets coming in unit time. Will it be close to 1? Calculator.
Point 125.
Point
125.
That's right. That's the way that is. So, even though there are 10 mean arrivals, actual probability of getting 10 arrivals in unit time is 0.125. Right. So, we can actually plot this and see, right, with respect to k, how this system, how this pans out. Okay. And the expected value of x is lambda, right. So, that is known, and if you want we can go back and derive that, right. So, expected value of x is lambda, which is basically number of packets per unit time, right. That is what the definition of the metric itself is. So, now the interesting thing is we would like to calculate the variance, right. Of the system. So, what is the variance of Poisson distribution? Lambda? Oh, in this case, okay, yeah, E of x is in this particular case, yes.
Variance also
Variance also lambda t. That's you derive that the other class, or you're guessing. This is much of derivation. You have not looked at the derivation for this one, right? So, variance is also lambda t, right? Okay, so that is the Poisson. We will visit this with respect to exponential later on. There are a lot of other variables like the negative binomial, beta and all that, which right now we do not need to look at, right. So that is a set of discrete random variables. Now we will go to I can get my spelling correctly. So for the continuous random variables, again you have your right PDF and CDF, your probability distribution or density function, and your CDF, right. So we look at a couple of things and we will stop at that point, right. So first is the uniform distribution, which is also there in the discrete case, but it is also in the right uniform distribution, which we will look at later. Then the more interesting one is your exponential distribution. So exponential again is very convenient for analysis, and can prove a lot of nice properties with respect to exponential, right. So we will look at that, the definition for exponential, which some of you might have seen in the other course, right. So what is the definition for exponential? Remember? What's the PDF for the exponential variable? Lambda equal lambda. Okay, I will not use lambda as a little bit confusing. Alpha, mu. We generally use mu because we find that actually it is 1 over mu, but we will write. So I will just use a e power minus ax. If you want, alpha is actually equally good. Okay. And the only condition is that x is positive, right, because I am looking at time between, usually this is used to model time, for example inter-arrival time between two packets, right. How do you model that? That is a random variable, and when it is described as an exponential variable you have some nice properties, right. So here a represents some parameter, just like lambda represents the mean number of arrivals, we will see what a represents. So what does a represent? Inverse of the mean, right. So the mean of this is 1 over a. So I guess some of you know and some of you do not know. Alright, so let us figure this out, right. So if that is accepted, right, sum of all the that f of x integrated from 0 to infinity goes to 1. So therefore that integration, do you still remember what is the we have our a here anyway, right. Is that right? It's been a long time since I did my integration. So therefore what does it work out to, right, this is a and this is 1 by a, so that is good, so 1, so that is right. Therefore we know that this will sum to integrate up to 1, so my e of x is e x e power r, right. So what is the mean of this distribution? What is the mean value taken by x? So again I guess I should have said that x and of course I forgot my dx here. So what is x e a minus ax integrate to? But your UV dv from the which is your u, which is your v?
X you can take u.
U is x. So then you do dd, it will become 1. I'll let you go through that misery later on and actually derive it, it will come to 1 over a, right. So that is why your expected a represents inverse of the mean, or your mean is 1 over a. Okay. So therefore E of x is, or I should not be saying E of x there, but anyway. Just say mean. And the variance 1 over a square. So pictorially what this looks like is, okay, so let a equals 10, which means if per unit, or the mean is 0.1 seconds, right, or whatever this unit is. So what does your graph look like? If you have to plot your f of x, right. So your starting value is x equals 0, okay. Doesn't sound right. Okay, for now we will just leave it to that. So it is here, right. Okay, so that is kind of what it goes to, right. As x goes to infinity, right, your value goes to 0. Now more interestingly, what is f of x? We will stop, we have to stop. What is f of x? Basically 0 dx, right. The summation of all probabilities from 0 to this value x, and that is equal to one minus e to the power minus eax. That is your f of x. So we will come back on Friday and look at why this is an important property in trying to show this so called memoryless nature of exponential, right. One thing we have not talked about is the properties, both Poisson as well as exponential, how they relate to each other, and how the memoryless property is actually going to be useful when we do a lot of analysis later on. We will stop here.
But when we do Poisson, then also we say it's memoryless.
Yeah, because the Poisson arrival implies that the interarrival is exponential. Yes. is exponential. So these two are tied together. So therefore, when I say Poisson is also memoryless, so is the interarrival time is also memoryless.
So by memoryless we actually means it is not dependent on what time that previous process has arrived.
Yeah, so what it means is, okay, we will have to formally state that, we will do that next time, but essentially if you have been waiting for the bus for half an hour, right, and you want to know what is the probability that the bus will come in the next 5 minutes. So that at the beginning of the system when you started waiting for this bus, that same probability holds even after having waited for whatever x number, for 1 hour and so on, right. So that is why the fact that you waited for an hour makes no difference at all. The probability of having to wait for another 5 minutes is going to be the same whichever point in time you look at in the system. That's your memory. That's where memoryless comes in, and that's where we'll try to use this to show.